The standard deviation is such a useful tool when dealing with normal distributions that is often used as a unit of measurement. For example, instead of saying that an SAT score of 618 is 111 points above the mean of 507, often one says that the score is one standard deviation above the mean. Moreover, instead of saying you scored 452 on the SAT, you might note that your score was 1/2 a standard deviation below the mean. When used as a unit of measurement in this way, the standard deviation is often referred to as a z-score. The formal definition of z-score is as follows. In a normal distribution, the z-score for a data point is the number of standard deviations that point lies above or below the mean. For data points above the mean, the z-score is positive, and for data points below the mean, the z-score is negative. Example 3. Recall that the mean SAT verbal score is 507, and standard deviation is 111. Calculate the z-score for SAT verbal scores of 650 and 320. Let's start with finding the z-score for the SAT score of 650. We are trying to find out how many standard deviations 650 is above the mean. To do this, let's first find the distance 650 is above the mean, and then we will compare this distance to our standard deviation of 111 using comparing division. The distance 650 is above the mean is equal to 650 minus 507, or 143. Notice this is more than one standard deviation, but less than 2 standard deviations above the mean. This means our z-score will be between 1 and 2. To find the exact z-score, let's divide 143 by our standard deviation of 111. 143 divided by 111 is approximately 1.3. Also note that since 650 is above the mean, the z-score should be positive. Accordingly, the z-score for 650 is equal to approximately 1.3. This is because 650 is approximately 1.3 standard deviations above the mean. Next, let's find the z-score for 320. To do this, we can use the same procedure as we used to find the z-score for 650. That is, first we will find the distance from the mean, and then we will compare the distance to our standard deviation using comparing division. Note that generally in mathematics, distance is communicated using a positive number. When working with z-scores, however, a negative z-score indicates to us that the data point is below, not above, the mean. One way to ensure a negative z-score for data points below the mean is to allow our distance from the mean to be negative. Thus, the z-score for 320 is found by first taking 320 minus 507 to find the distance 320 is below the mean, and then dividing this negative quantity by our standard deviation of 111. When we do this, we get our z-score is approximately equal to negative 1.7. In summary, the z-score for 320 is approximately equal to negative 1.7. This is because the data point 320 is 1.7 standard deviations below the mean. We can find the z-score for any data point by subtracting the mean from the data point to find the distance the data point is below or above the mean, and then dividing that distance by the standard deviation. Notice the data point minus the mean will be a positive number when the data point is above the mean, but it will be a negative number when the data point is below the mean. This will ensure that our z-scores have the proper sign. Note also that when we calculate the z-score, we typically round to 1 decimal place. Recall that in a previous section we discussed quartiles. There's a more general term, percentile, that tells how a data point is positioned in relation to other data points in a normal distribution. The percentile for a number relative to a list of data is the percentage of data points that are less than or equal to that number. For example, the median is always the 50th percentile because half the data are below the median. Similarly, the first quartile is always the 25th percentile because 25% of the data are below it. And the third quartile is always the 75th percentile because 75% of the data are below it. Example 4. According to the histogram to the right, the percentile for the SAT verbal score of 660 is equal to 91.6 because 91.6% of the test scores are less than or equal to 660. One consequence of the 68, 95, 99.7% rule is that we are able to use z-scores of data points to approximate their percentiles and vice versa. Table 6.2 below gives the information needed to calculate the percentile of a data point given its z-score. For example, a z-score of 0.5 corresponds to a percentile score of 69.15. And a percentile score of 93.32 corresponds to a z-score of 1.5. Furthermore, a z-score of 0 corresponds to a percentile score of 50. Also notice that negative z-scores correspond to percentile scores that are less than 50, and positive z-scores correspond to percentile scores that are greater than 50. Before moving on, you should consider why this is so.